And with that, good morning everybody. Welcome back to Calc 1. Plan for today. Promised to have a Standard 17 quiz for you. Then we're going to finish off Standard 18, talking a little bit more about area approximations. And then if we have time towards the end of class, we'll jump into Standard 19 and start talking about the FTC. My next office hours are going to be on Monday. I'll have my morning office hour from 11 to 11:45. I'm not sure about if I'll be able to do my afternoon office hour Monday. I'll let you know Monday morning. I've got factors that may, I don't know what my schedule Monday afternoon is going to be like. So, post another web work due on Wednesday. Quiz Monday over Standard 18. Any questions or comments before we get started for today? What do you call a number that can't sit still? You call it a Roman numeral. And that is quiz time. Hint, if you're having trouble visualizing this, I put a picture on the board. go ahead and take a few seconds to finish up your thoughts. And with that, pass your quizzes in, please. Quizzes in, please. Thank you. And thank you. Alrighty. So when we left off last time, we were in the middle of Standard 18, where we were talking about how do you find approximations for areas of weird shapes. And the idea, yes?
Do you have any more Standard 18 factors?
Nope. It is online on campus though. Where the main idea is we took an area under a function, like let's say we wanted to approximate the area under f of x equals x squared from 1 to 5. And we said, well, that's a weird shape. It's hard to find the area of something like that. So what's something that we can use to approximate the area? Well, rectangles. Rectangles are relatively easy shapes to find the area. We just need to multiply width times height. And so the idea for finding the area under, say, f of x equals x squared from 1 to 5 was, let's split that region up into rectangles and add up the areas of the rectangles to approximate the overall area. And we kind of talked about two different ways to do that, with a right endpoint approximation and a left endpoint approximation. Where the idea with the right endpoint approximation is if you want to use, say, R4, an approximation that uses 4 different rectangles, we split the region up from 1 to 5 into 4 equally sized pieces, so that the width of each rectangle is going to be the length of the region, 5 minus 1, divided by the number of rectangles, so 1 for instance. The height of each rectangle, well, if we're doing R4, we set the height of the rectangle to be equal to the y value of the function at the right endpoint of each rectangle. So, for instance, our first rectangle goes from 1 to 2. So it's going to have a height of f of 2, which is, if you plug 2 into the function, will give us 4. Similarly, with our second rectangle, we plugged in the right endpoint of the rectangle from 2 to 3, so 3 into the function to get f of 3 for the height of that rectangle, and so on. And then ultimately, what we did was we took width times height for each of the rectangles to get the area of each one. We added them all up, and in this example, we got 54 as our answer. Similarly, you could do what's called a left endpoint approximation, which is set up the same way, but you use the left endpoint of each rectangle you plug that into the function to tell you what the height of each rectangle is going to be. So for instance, first rectangle goes from 1 to 2, just like up here, except this time we plug in f of 1 to get the height of this rectangle, and then f of 2 for the second, f of 3, f of 4. And when we did that approximation, we came out to 30. And what you all had decided last time was that you thought the actual area should be in between 30 and 54. That 54 was probably too big because rectangles included all the area that we needed and then some extra, like this extra kind of little snippets up here and so on. Whereas you all said that you thought the left endpoint approximation is probably an underestimate because the rectangles in this case didn't include any extra area, but they also didn't fill up the whole area that we wanted. There's still these sort of regions here, where I'm going to draw my X's, that are unaccounted for. So you all said the actual area was probably less than 54, but greater than 30. What can we do if we wanted to get an even more accurate approximation? We did this with 2 rectangles, and then we did it with 4 rectangles, and we said the 4 rectangle approximation is probably better than the 2 rectangle approximation. Nolan? I just called you Nolan. Jonah, what do you think? I'm sorry, Jonah.
You're good.
One of those mornings, huh?
No, that's not it. Add more rectangles.
Add more rectangles. You could split it up into 8 rectangles, or 16 rectangles, or 500 rectangles. And the general idea, this is 1, this is 5. We want to approximate this area. The more rectangles that we use, the better an approximation we'll get. So if we use a whole bunch of rectangles, the rectangles are going to stick pretty close to the curve and have very little extra area compared to what we have currently with 4 rectangles, say. Y'all want to know something fun? If we wanted to find the actual area, something we could do is we could use right endpoint approximation within rectangles, and then take a limit as n goes to infinity. Because if you take the number, if you let the number of rectangles get bigger and bigger and bigger, the right endpoint approximation, and for that matter, also the left endpoint approximation, will give you better and better approximations for the actual area. Some of you are giggling at this. You know what's coming up in the next standard, don't you? So any questions or comments before we look at a second example of applying this process to a particular function? So in that case, let's do another function. So I want to look at the function. Not that packet. Here we go. I want to look at the function g of x equals 25 minus x squared from 0 to 4, which is going to look something like this. And I want to approximate the area underneath the curve. G of x equals 25 minus x squared from 0 to 4. So, what I would like for you all to do is I want you all to go ahead and take a couple of minutes, see what you can find for this function. Specifically, I want you to find L4 and R4 for me. Let's go ahead and find a left endpoint approximation using 4 rectangles and a right endpoint approximation using 4 rectangles for this area. And we'll come back together as a class in a couple minutes and see what you all found. But as always, encouraged to talk to each other and or flag me down with questions. They're partying out there. As always, if you're not quite sure where to start, feel free. I encourage you to talk to the people sitting around you and or flag me down. Happy to give some tidbits. If you think you found L4 and R4, try thinking about answering the two questions at the bottom of the page as well of the packet. Namely, are these over or underestimates, and how could you do better? So basically, this is, you're finding the area under the function. You're adding them all up. In this case, you've got an interval of length 4, and you're using 4 rectangles, so each one's going to have a width of 1. Well, not necessarily. So let's think about it like this. Let's look at your first rectangle. If you're doing a left-hand approximation, then the way you would find the height of this rectangle is you go to the left-hand point at x equals 0. You would put that in the direction. Yeah, 25 minus 0 is 3. And that would be the height of your first rectangle. And there's the second rectangle. It's yeah, and then basically you repeat the process, and then technically you need to multiply each of those by the width, because that's the width is 1 in this case. That doesn't matter. So yes, that's the right idea. Well, keep in mind, you only need 4 of these. But 4 rectangles are 4, so you would set G of 3. From the right, you would just use the right midpoint of each rectangle instead of the left. So. Let's give it about 1 more minute, and then we'll come back together and discuss this as a class. Good, you seem like you're having fun.
It's Friday.
What's not to love?
Exactly.
Alrighty, let's come back together and talk about these. So I'd like to start with, so we're looking at L4 and R4, and in both cases I think the widths of our rectangles are going to be equal to each other. So how do we find the width of each rectangle? Emma? Yeah. You can always find width by taking length of the interval over the number of rectangles. So I'll write this over the side here. So in this case, we could say that the width is going to be of interval divided by the number of rectangles. To find the length of the interval, you can always just take your far right point minus your far left point to get that. So in this case, it would just be 4 minus 0. Number of rectangles, in this case, is 4. So I think we're going to get a width of 1 for each of our rectangles. So we'll have them from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 0 to 1 to 2 to 3 to 4. And how would we find the height of our first rectangle if we're doing L4? Alright,
You can plug 0 into the f of x equation.
incorrect. You would plug 0 into the g of x formula. Change the function name on you. But yeah, that's it. But yeah, that's exactly it. So we have our first rectangle goes from 0 to 1. If we're doing a left endpoint approximation, we look at the left endpoint of that rectangle, which is at x equals 0. Plug that into the function g of x, and our first rectangle will have an area of width times height, which is 1 times g of 0. Our second rectangle goes from 1 to 2. It's going to have a height of g of 1, since we're doing a left endpoint approximation. So I'll get 1 times g of 1, A3, our third rectangle, with 1, height g of 2. And finally, our last rectangle will have a width of 1 and a height of g of 3. And so then you basically just need to plug in 0, 1, 2, and 3 into the function g of x, which will give us 25 minus 0 squared, 25 minus 1 squared, 25 minus 2 squared, and 25 minus 3 squared. All of these being multiplied by 1, but since it's being multiplied by 1, we don't actually need to do anything there. Which, we add those up, we'll get 25. 1 squared is 1, 25 minus 1 is 24. 2 squared is 4, 25 minus 4 is 21. And 3 squared is 9, 25 minus 9 is 16. Which is, oh gosh, 49 plus 37, 40 plus 30 is 70, 9 plus 7 is 16, 70 plus 16 is going to be 86 is what I'm getting for our L4 approximation here. Any questions or comments related to that? So R4 is going to be pretty similar. We're going to take the sum of the areas of 4 separate rectangles. What's going to be different about R4 from L4? Meaning, what do we have to do differently, James, in order to get a right endpoint approximation as opposed to a left endpoint?
The summation is not going to include 1 times g of 0, but it is going to include 1 times g of 4.
So you're saying it's 1 times g of 1, 1 times g of 2, 1 times g of 3, 1 times g of 4 instead?
Yeah.
I like it. Yeah. Our first rectangle goes from 0 to 1. When we used a left endpoint approximation, we used the left endpoint of that rectangle and plugged it into the function to get a height of g of 0. But now, our first rectangle is going to have a height of g of 1, where 1 is the right endpoint of that rectangle. Second rectangle goes from 1 to 2. If we use the right endpoint 2, plug that into the function, we'll get a height of g of 2. Third rectangle goes from 2 to 3, plug in 3 into the function for that height. Fourth rectangle goes from 3 to 4, has a right endpoint of 4, so we'll get 1 times g of 4. And the width of each rectangle is still going to be the same whether we're doing a left or a right endpoint approximation. The width is still going to be length of the interval over the number of rectangles, so we didn't need to repeat that computation. So that's going to give us 25 minus 1 squared plus 25 minus 2 squared plus 25 minus 3 squared plus 25 minus 4 squared. Just plugging in 1, 2, 3, 4 into our function, g of x, which is 25 minus 1 is 24, 25 minus 4 is 21, 25 minus 9 is 16. In fact, it's the same three numbers we had up here. The only difference is we're not using the 25. Instead, we're using 25 minus 4 squared, which is 25 minus 16, I believe, is 9. Which in the end is going to give us 45 plus 25, and I'm getting 70 for my right endpoint approximation here. Katie.
I know we didn't have to do the R2 and L2, but for those then, instead of the 1 in the front, is it a 2 in the front?
Yeah, so if we wanted to do, like, let's say L2, for instance, in this case. I'll draw it out here on the side. Let's say this is going to be 4. What we would have to do is we would divide up length of the interval over the number of rectangles, and what that would give us is interval is length 4 still, but the number of rectangles is 2, so the width of each rectangle would end up being 2 in that case. So we'd have one rectangle from 0 to 2, one rectangle from 2 to 4. And if we did, let's say, a left endpoint approximation, get something that looks like this. If we wanted to do L2, what we would have to set up is area of the first rectangle, area of the second, which is 2 times, what's the height of the first rectangle? Well, that's just f of 0. Oh, excuse me, g. Sorry, Reagan, I already got on you about that. What would be the height of the second rectangle?
Is it 2?
Is it what?
2?
It would be g of 2. Yeah, you would plug in 2 into the function, because the first rectangle goes from 0 to 2, has a left endpoint of 0. Second rectangle goes from 2 to 4, has a left endpoint of 2 instead. And then that would give you, what, 2 times, what's g of 0? That's 25 minus 0 squared is 25. G of 2 is 25 minus 4 is 21, which would give you 50, 42, and I would get 92 is my answer. And then R2 would be very similar. You'd have 2 times g of 2 plus 2 times g of 4, if you wanted to compute that. So, question is, if we're looking at the graph of L4 here, is L4 going to give us an overestimate or an underestimate? Just looking at the graph of the function. Katie,
Overestimate?
why do you say overestimate?
Because the rectangles go outside the curve, and so they're gonna.
Yeah, they include everything we want and then some. So in this case, I would say L4 is going to be an overestimate. And Jonah, how about R4?
That's a underestimate.
Yeah, it's going to be an underestimate for similar reasoning, except this time the rectangles don't include everything that we want them to include, but they also don't include any extra. Any questions or comments about that? question, or Nora's question.
If you take the overestimate and add it to the underestimate and divide by 2, so you're taking the average, would you get a more accurate value?
I would probably give you an accurate value. So basically what that would give you here is the midpoint of L4 and R4, which would be 1678. That would give you a more accurate answer. It wouldn't necessarily give you the exact answer, but that would certainly be a way that you could sort of combine L4 and R4 in a way to get a more accurate value than either one individually, I would agree. Because the fact that this is an under and this is an overestimate tells us we already know the actual area should be somewhere in between 70 and 86. Finding the midpoint of that interval is probably a pretty good guess for what the actual area would be. What is the actual area? Speaking of which, I already computed this. Spoiler alert, we're computing the actual area next standard. The actual area comes out to 78 2/3. If you're curious, which we will see later on. Okay, I have a question though. In the first example we did, R4 we said was an overestimate, and L4 was the underestimate. In the second example, L4 was the overestimate and R4 is the underestimate. So why is that? What's different about these two graphs or these two functions that would cause, in one of them R4 is the overestimate, but in the other one L4 gave us the overestimate? What's different about maybe the shape of the functions, John Minnie?
The first one has a positive slope, and the second one has a negative slope.
So you're saying you think it relates to the slope of the function, being positive versus negative?
Yeah.
James, what do you think?
Yeah, I was gonna say that the first one is increasing when the second one's decreasing.
Yeah, so if we look at this function, this is our f of x equals x squared is an increasing function. Or in other words, it has a positive slope, a positive first derivative everywhere. And the fact that it's increasing is going to tell us that the right endpoint of each rectangle is always going to be higher up than the left endpoint. Because as we go from left to right, the function's getting bigger. So if you look at using the right endpoint of each rectangle for an increasing function like this, the right endpoint always above the left endpoint and everything else in between. So using the right endpoint to help us approximate the area is going to give us a approximation that's a little too big. The rectangle is going to include everything we need and then some. Whereas if we contrast that with L4 in this case, the left endpoint is always smaller than the right endpoint and all the points in between. So using that to find our height is always going to give us an underestimate for this increasing function. But if we contrast that with this function over here, g of x equals 25 minus x squared, this is a decreasing function. As we go from left to right, the function is going down. And that means the left endpoint of our rectangles are going to always be higher than the right endpoints of the rectangles, which will give us a larger y value or larger height and give us sort of the extra area in this case. Whereas the right endpoint for this decreasing function is always going to be lower than the left endpoint, and so that'll lead to R4 being an underestimate, whereas in this case R4 turned out to be an overestimate. Yeah, Katie.
So it doesn't really matter what x equals 0, x equals 4, or x equals 1, x equals 5. It's just whether it's a positive f of x or a negative f of x.
Not a positive or negative f of x.
Well, then like the negative x squared or the positive x squared.
Yeah, I would say what ends up being important here is the fact that f prime of x is positive over there and f prime of x is negative here.
Okay.
Because as we kind of saw in the last few standards, what it means for a function to be increasing is that f prime of x is a positive number, and what it means for a function to be decreasing is that the derivative of your function is negative. So let's sum up what we just said. I'm going to write this on the sideboard here. I'm going to skip the next page, leave that to you as a kind of a practice problem if you'd like. But in general, we can say that Rn is always going to be an overestimate if f prime of x is greater than 0 on the interval, and an underestimate if f prime of x is negative on our interval. Meaning if f prime of x is positive, so the function's increasing, then our right endpoint approximation will give us an answer that's a little too big. But if f prime is negative, we have a decreasing function. Using the right endpoint approximation will always give us an underestimate to work with. On the other hand, we can say that L sub n is going to basically be the opposite of that. It's going to be an underestimate if f prime of x is positive on the interval, and L sub n is going to be an overestimate if f prime of x is negative. So depending on whether your slope of your function you're looking at is positive or negative, that's going to tell you whether you have an over or an underestimate to work with. Any questions or comments about that? So I have a question. What if f prime is sometimes positive, sometimes negative? So like what if, for instance, we had a function that did something like this? And let's say we wanted to go from 0 to 6, where the slope's sometimes positive, sometimes negative, and we were to do like a left endpoint approximation. Would that be an underestimate or an overestimate, do you think? Or is it hard to tell? Morgan?
It's hard to tell
Why is it hard to tell?
because some of the rectangles are overestimates and some of them are underestimates.
Yeah, some of the if f prime changes from, or if f of x goes from increasing to decreasing, or vice versa, then some of your rectangles will be not enough area, like these first few. But then when the function switches to decreasing, suddenly they give too much area. And so if we want to ask the question, is L, I don't know, 6 an under or overestimate? I would say it's hard to say. So the moral of the story is, if f prime is always positive or always negative over the interval that you're looking at, then you can say for sure whether Rn and Ln give over versus underestimates. But if you have a function that sort of does some wavy shapes, then meaning f prime is positive sometimes and negative sometimes, then it's kind of hard to say, and you can't really say whether r sub n and L sub n are over versus under estimates, except on a case-by-case basis. I would say it's kind of ambiguous, so to speak. Any questions or comments about that? How are y'all feeling this morning? Y'all doing okay? Y'all tired? Y'all ready for Thanksgiving break? I am as well. Have a good day, everybody. So that's it for standard 18. Just so you all know, the homework I posted, homework 22 I think, is on the standard 18 stuff. So I encourage you to check that out over the weekend so you'll be ready for Monday's quiz.
Okay, Dr.
What's up?
So what is things that you bring up? Was it that Wednesday or nothing?
Oh yeah, you're not actually in the college. You know, they're probably great. So we're gonna have class next Monday, and then that'll be it. So no class next Wednesday or Friday.
Okay.